to play T-shooters, so I feel like I'm letting everyone down always.
No, that's why you have to stay.
Hello.
Valerie is not the one.
Hey!
Hey.
You guys have to click something that's happening.
Welcome back to Ops 2023-2024 lecture 7. Woo! Okay. So we had an event yesterday, the work session. If you came, that's cool. If you didn't, that's also cool. Sorry for any troubles you're having with the project. The HTO5 is absolutely abysmal, and it has so many bugs. But if you have been trying and yeah, I appreciate your effort, and I really hope it didn't make you too frustrated.
Yeah, thank you a lot for your patience. I know I saw quite a few of you either in the lab today or at work session yesterday. There were a lot of connection issues, which is fine. My computer doesn't connect to HTO5 itself, so yeah, thank you for putting up with that. And for coming to 2 ops events in a row.
Yeah.
You know, it's a lot for you guys, for us as well. We're excited.
Yeah. Yeah, and also don't be concerned about, well, I'm not concerned, but we're wearing masks because one of a different officer got COVID, and we were in contact with them, we were in the same room as them yesterday, so we're just wearing masks just in case.
Officer meeting, so now all of us are just taking precautions.
Yeah, so if you want to wear a mask, you can, but we're also probably okay because we're quite far. Yeah. Okay, so has everyone signed in? Would you guys vote for your favorite game? If anyone wants to say. Why?
Valerie.
You put Valorant?
Yeah.
I see.
Not proudly.
No, not proudly. Hey, League is the one with the barking face.
League is the one that people put not proud. Valorant is fine.
Valorant is okay. Yeah. Well.
Game preference,
Okay. So before we get started, some reminders / announcements. So today is our last lecture of the quarter. So our next 3 events will be, well, 2 of them will be work sessions, and then the last one will be the competition for Game Guino. So for Project 4, we have a competition, iPodino, where people create little different songs. For Game Guino, you're gonna need a game, which you can actually display on a little screen. And so basically the competition is just, it's very lighthearted competition where everyone makes their own game, and then you can play each other's games and just, have fun with it, and whoever has the coolest game gets a prize. And so because it's a pretty big project, the base thing that you turn in for actually ops, the competitions are always optional, but the base project is actually already pretty complex, and so we have 2 work sessions in which we give you 6 whole hours of our undivided attention. Also our lab hours, obviously, but so we're gonna have 2 work sessions the next 2 Thursdays. The 7th is also a Thursday, probably. So I recommend going to both if you can. If you need help outside of that time, obviously we have lab hours, and also we are available through PM, Discord, email. Yeah. But just to reassure people, this has 75 or 80% less bugs than the HCO5 project. There's nothing that will really go wrong besides if you wire stuff wrong, and obviously that's pretty simple to fix compared to your computer simply not detecting an HCO5, right? Yeah. So that's about the competition.
Yes, so next, IEEE officer elections are quickly approaching. That means that we have a new round of officers, including ops leads, so I highly encourage all of you to think about potentially becoming an ops lead. Now I might be thinking, oh, what's the time commitment like what do I need to know for this role, yada yada. In order to answer all of those questions and more, there's an officer session that is coming up Friday, March 1st at 6 p.m. They haven't figured out the location quite yet, so we'll announce that probably at our next event next week. But in the meantime, feel free to always ask Laura and I any questions. I don't know, maybe we can do something as well where any questions you have about ops itself on the technical or logistical side, we can answer those as well. But I think the main thing probably is if you feel maybe you don't know enough, or maybe you don't feel prepared for it, please don't let that be an obstacle to you applying. That's exactly how Laura and I felt and how the previous 2 leads felt. A lot of it you kind of pick up as you go, which is completely fine. That's it's there for every role. So please do consider applying.
Yeah. It's a really awesome position, job, I don't know, I'm sure Adrian agrees, but I personally find it very rewarding to help people, so if that's something you like, I would suggest. And then, yeah, like knowledge of how well you know things is probably like the least in priority in terms of what you need in order to be a good ops lead if you're nervous about like, oh, will I make it or not, right? Ability to talk to people, help people, like give lectures like this, work on the fly if things are going wrong. Like that's what's more important rather than actually being knowledgeable. So please do not feel intimidated by like any like knowledge prereq. Yeah, so it's gonna be next Friday at 6 p.m. So I hope you can make it. And also like obviously if you want to also go in case you are thinking about applying to other IEEE officer positions. Obviously there's ops lead, which you should, but there's also workshops, which a lot of people think about if they're a first year. There's also all the admin roles of like treasurer, no, that's executive, events coordinator, secretary, etc. You know. So if you are thinking about it, I would highly suggest coming. Any questions? Yes.
If we can't make the meeting, is there like info sent out?
Good question. We'll get back to you on that. I want to say tentatively yes. I think
If
it makes
it's-
sense that they'll provide a bunch of resources for that.
If you have questions regarding ops, you can just come talk to us.
Yeah.
If you have questions regarding the other roles, you can also come talk to us, probably, and we can like give as much information as we have. But obviously we can also link you to like, let's say you're thinking about becoming this certain role, and you can be like, oh, I think I want to be this role. We can like direct you to the person who is currently like that role this year.
Yeah.
Yeah. But if it's about ops, like obviously we're here always for you guys. Good? Okay.
Okay, that being said, I mentioned this last lecture as well. We'll be going a little bit deeper into communication protocols for this lecture. These won't be strictly like too important for your next project, and that's not critical for you to know like all these and outs of how I2C works for you to be able to build Gameweino. This is just for kind of, you can think of it for educational purpose, you know, kind of roughly how these different communication protocols work, where they might be used, etc. Oh yeah, I'm sorry. The second part of this lecture, we'll be going briefly into some of the actual coding parts that would be helpful for Gameweino. We did mention, I think, at one point that Gameweino, a lot of it is kind of the code. It's much easier to debug hardware-wise. There, I think, are just two like critical components that you need, and then after that, how far you go with the project is a question of like how much you want to code.
Yeah. So we'll be talking about communication protocols, which is kind of a lot of information thrown at you at once, and then a little bit of coding. If you're in CS 31, 32, if you've taken like something in high school, or if you have no coding experience at all, it shouldn't be that bad. So I don't think anyone should be scared about the coding aspect. Okay, so communication protocols. So we talked about this a little bit in our last lecture, but we kind of just threw that at you and we're like, okay, well, we're gonna move on. But now we're gonna get into it a little deeper. So a communication protocol is basically just the way that a microcontroller talks to an integrated circuit. So the devices we've been using in our projects, like the HC05, the 555 timer, eventually we're gonna have something called H-bridge. All of these are integrated circuits, and if you remember what that is, it's kind of just a circuit that's very complex but packed into a very small chip, so you can use it for more things. And so the way that microcontrollers actually talk to these integrated circuits is a thing called a communication protocol, and different integrated circuits have different ones, and different microcontrollers use different ones. And so these are just standardized ways that they know how to talk to each other. Because if there wasn't this standardized way, they'd have no idea what actually the other device the other device is sending or wants to be sent, or just how to communicate in general. And so we have a few terms that we want to go over before we talk about specific communication protocols themselves. So first is we have a clock signal. And so clock signal is just simply signals high, low, high, low, high, low. And we can use that signal to basically create a clock that helps us keep track of the data we're sending. So that's the clock signal. And then there's asynchronous and also synchronous. These are different types of communication protocols. Asynchronous is the graphic on the upper graphic. Basically, for an asynchronous signal, it doesn't require a clock, it doesn't require any sort of timing to send its data. Instead, the data that it sends is packaged between other specific data that tells you when to start and stop sending data. And so we're gonna get into it a little bit more, but basically you have the actual data in the middle. Beforehand, you have a bit, which is just a very small summation, like a bit, like it's either a 0 or a 1 in terms of the actual like computer, but or like the device. So we have a start bit, we have the actual data, then we have a stop bit. So the start and stop bit just kind of indicate when to start and stop sending data. And then we also have a parity bit, which is not shown here. And then for synchronous communication, that's when you actually have a clock, and the clock keeps track of when you're sending data and says, okay, in this region of time, we're gonna be sending data, otherwise, no.
Just to go a little bit more into that, we'll also be covering this in later slides, but I think this diagram is kind of probably a bit more clear than some of the ones that might come later, so I'll quickly take the time to explain a little bit. What's happening here is basically this. Typically you'll have two controllers, let's say, two separate devices. One would be the controller, the other the peripheral. The controller would control the clock, right? The actual signal that kind of supposed to synchronize when data is sent and received. So what's happening here is basically there are little arrows here that indicate when the clock signal changes from low to high. These are referred to as edges. So one of the conventions that's used here is that data is red, meaning the data here is on the data line. There's two separate lines, one for the clock, one for the data. So data is red when the clock changes from low to high, i.e. on a rising edge. So that's what this green line is supposed to indicate, that, oh, when the clock changes from low to high here, you read a 1, because the data line is high. If you go a bit further, let's say to this bit here, again the clock changes from low to high, you read a 0.
Questions on that? Okay, and then the last couple terms, the baud rate, we've been talking about that a lot since we've been using the Arduino and also the HC05. It's simply the rate at which information is sent out or received. For HC05 and Arduino, it's been 9600. We're not going to be using any other baud rates in ops, but yeah. And then we have bandwidth, which is just like the maximum data rate that you can have for a device. Yeah. So now we have a couple more terms. We have serial versus parallel. So a serial communication device, you're going to have data that's sent one at a time. So if you have, like, let's say you want to send several bits of information, or that's not bits, like in the actual sense, but let's say you have several things you want to send over through your communication line. For a serial communicator, it's going to send one at a time. So I'm going to send the word cat, and I'm going to send the word dog, and then like that. Serial is generally slower because obviously you have to wait for each thing to be sent separately in a row. You can kind of think of it as like resistors, you know, they're in series. Anyway, but besides being slower, it has the advantage of it's a lot less likely to be corrupted because the device is only managing, say, one thing at a time. So this is better for long distance communication. And then secondly, we also have parallel communication, in which all the data is sent at the same time, and you need more connections to be able to actually be able to interpret all the data. As you can see here, like if you're sending like 7 things all at once, you have a lot more interpreters to be able to send and receive. And the pro of this is obviously that it's faster, you can send all your things at once, but it's a lot more easily corrupted because when you're sending many things at once, it's hard to tell, like, oh, what if something goes wrong in the middle? Which thing went wrong and stuff like that. Okay, are we good there? Okay, and so getting into our first communication protocol. So we're gonna go over 3. The first one is UART, and is the one that you should probably be a little familiar with, not in the sense of like actually what it is, but you've heard of it because Arduino uses it. So UART stands for Universal Asynchronous Receiver Transmitter, and as you can see in the name, it says asynchronous. And so we just went over what asynchronous means in the sense that it's a communication protocol that does not use a clock, right? And so what's also very important about the UART communication protocol, it has exactly one controller and one peripheral. So as in one person who like controls what is happening, one person who receives what is happening, if you want to put it that way. And so if you remember with the HC05, because it was operating under the UART communication protocol, when you were communicating from the Arduino to the HC05, you couldn't use the serial monitor because there was only one controller and one peripheral. It's 1, 2, 1. So as in when the controller is in contact with a peripheral, it can't being contacted with a different peripheral, which would be like the serial monitor, if that makes sense. And so for asynchronous communication, we have to have a baud rate, in which you've seen we set it to 9600, and then instead of the clock signal, we have the start, the stop, stop, and then the parity bits that indicate your data. And so I went over it a little bit, but like there's the data at the start, there's the start bit, at the end there's the stop bit, and then the parity bit basically kind of just is a indication of whether the data was set correctly. It's gonna say, the parity bit is either a 0 or 1, right? And so it's either gonna be set to 0 or 1 depending on the actual data itself. And then the peripheral can interpret that data and see, oh, does my data match whatever the parity bit is telling me? If not, I know that data was set wrong, or somewhere along the line, that data was corrupted. And so the parity bit, it's like, this is like too much detail necessarily, but it's gonna be set to 0 if there's an even number of 1s in the data, and 1 if there's an odd number of 1s. And so the peripheral can like count the number of 1s and say, oh, if the parity bit says 0, I know there must be an even number. And if I see an odd number, I know that the data was corrupted. But that's like a little unnecessary for us to know.
Basically, to summarize, yeah, the parity bit is essentially just an extra bit that's there based, and it's set to 0 to 1 based on what the data itself is, so that when the transmitter sends out data to begin with, it'll have a specific parity bit. Then, based on what the data they send is, the receiver can check then, okay, if I do the same kind of calculation, I should get the same parity bit. If the data changes somehow en route to the receiver, then they might get a different parity bit, and at that point they know, oh, the transmission messed up, I didn't receive the data correctly.
Yeah, and then for physical wiring, generally, so each device is gonna have an RX and a TX pin, and you just have to connect each one to the other device's opposing pin. So like so device 1's RX pin to device 2's TX pin, and then vice versa. That's what we did for the HC05, except that we didn't draw in, like this graphic doesn't have the voltage divider in this circuit, but we had the voltage divider there if you remember. And then you also need a mutual ground. So this is kind of the entire just like physical wiring. There's not much more that you need to do. Okay, and then a little bit more of UART in action. This looks a little complicated, but it's just gonna be like a small summary of how UART works. And so for UART1, like our first device, we have the transmitter or the controller. The transmitter has the data that we want to send to the other UART device through the data bus, which is kind of just where the data actually goes in terms of a physical place. And the transmitter takes the data, it adds the start, stop, and parity bits in order for the receiver to correctly interpret it. And then at the TX pin, it sends the data out at a certain baud rate. On the receiver's end, it samples data at the RX pin because, as you remember, or as we just said, that the TX and RX pins are connected on the opposing ones for the other device. So it samples the data at the RX pin from the start to stop bit because it recognizes what those are at that certain baud rate. And then after it does that, it's like, okay, if the parity bit checks out and then we know that the data isn't corrupted, we can remove the unnecessary bits that don't actually contain our information and then do whatever we need to do with it. So that's just kind of the process. Does this make sense? Any clarifying questions? Okay.
Yeah, so now for our next communication protocol. This one is serial peripheral interface. This is part of what allows you to control like multiple devices with one device. So let's go through it. First thing to note, this is a synchronous communication protocol, meaning that you would have kind of at least 2 lines. You need one to kind of carry the clock signal to synchronize when you send and receive data. The part I mentioned about, for example, like taking data at the clock's rising edge. And then you get another kind of line in order to actually send the data itself. So the way that this is kind of controlled, I mentioned earlier again that the controller, the device that's sending out data to begin with, or I guess you could think of it as like your main device, that would be actually sending out the clock signal to begin with. It's generating the signal, and then from there, you actually you can change the clock signal based on when you want to start and stop receiving data, so that the peripheral knows when it should kind of read or write data. The benefit to this is that you don't need a separate start or stop bit. You can think of it as kind of, if you are in a room with another person, you want to talk to them, you need some way of getting their attention first. And then similarly, when you're done speaking to them, you can like, I don't know, say goodbye or whatever. So that would correspond to like your stop bit. With a synchronous communication protocol, there's no need for all that, because as soon as you start sending out the clock signal, if you make some sort of change to how the clock signal is, then the peripheral knows, oh, there's been a slight change, it's time to start reading data. That being said, there are a couple of conventions and acronyms that'll come up a lot, so I'll go through them now. You'll see COPI here, that's controller out, peripheral in. Again, your controller is the main device. Think of it as if you have a laptop connected to a keyboard and mouse, your keyboard and mouse are the peripherals, laptop is the controller. So COPI, controller out, peripheral in, corresponds to the TX pin, the transmitter pin. The other one, controller in, peripheral out, corresponds to the other pin, the receiving pin. These come with other names. I won't go through those. I'll probably just continue to refer to them through these two acronyms here. There's also the actual clock wire, SCLK, and then there's a chip select, which I'll get into shortly. Oh, I should also mention, by the way, that there is an alternate, unfortunate naming convention for some of these devices. It's master and slave. I'm going to be using controller and peripheral for reasons that I hope should be pretty evident. Okay, so let's go through how this works. The first thing is that with SPI, you can control multiple devices at one time. There's a name for this that I don't exactly remember, but the idea is that when you have multiple devices, each one has a certain address, and you also need to be able to kind of tell the peripheral when it needs to start reading data, when it needs to wake up and start listening for signals from the controller. That is done via the chip select pin. So the idea is that the controller will take one of those specific lines to one of the devices and bring that chip select pin low. Then the peripheral knows, oh, it's time to start reading data. And at that point, your clock signal starts and you can start sending data, be it an address or some other piece of information that you actually need to send. And then this is done, this data is read in the usual way that I described before, where when the clock goes from low to high, you'll look at what the data line reads, whether it's a 1 or a 0. You keep going until you until the data itself is actually sent. Again, you don't need a stop bit for this, so there's a convention as to how much data is sent at one point. Oh, and yes, when the actual communication itself stops, the chip select pin goes back to high to correspond to the fact that, oh, the peripheral no longer needs to read data. Are there any questions at this point? Okay.
Okay, so that's it for SPI. Lastly, we've been talking about I2C. SPI, from what I recall, we don't actually use ever in our in ops, but I2C we do, including this little OLED thing, which we'll be using for Project 5. And so I2C stands for integrated circuits. It's a little confusing because it sounds like IC, but there's a 2 in there. But the I is like I squared, like 2 I's, you know. Anyway, and so for I2C we have multiple controllers and multiple peripherals. So instead of just one controller and then like a bunch of little minions, we have multiple controllers and multiple peripherals. And so a controller can call a peripheral using a peripheral address, same with SPI.
Yeah.
Sorry. And then also in common with SPI is that there is synchronous communication, which, as you remember, uses a clock signal. And so for the physical wiring of I2C, we have this little diagram. We have the SDA pin, which stands for serial data. At this pin, SDA, the controller and peripheral receives and sends data. And then we also have the SCL or SCLK, which is the serial clock, in which it carries the clock signal generated by the controller. And so, as you can see here, we have 2 different lines, or like 2 different sets of controllers and peripherals. So this controller has the SDA, in which it's communicating with peripheral 1, and also communicating with peripheral 2, because as you can see, there's a wire here that connects the 2 SDA lines. And then there's also the clock that connects controller 1 and controller 2 to both peripheral 1 and peripheral 2. So a lot of communication, basically. And so a very quick summary of how I2C actually works. And so what happens at the very start, or the start condition, is that the controller brings SCA to low, and then also switches SCL to low. And then after that, because if each peripheral has a unique address, the controller has to find the peripheral that it wants to communicate to, has to find the address in like a data sheet, not like the actual data sheets, but you know, in their data that they have, they can find that address. And then there's a read and a write bit in which you can switch to either high or low depending on whether it wants to request or send data. And then lastly, no, sorry, not lastly, but next is the ACK and NAP bit, which sounds kind of funny, but it's generated by the receiver after it has already received, or like after it has already received the request to send data or to send the request to receive or send data. And then the ACK and NAP bit, basically the receiver generates that to indicate whether the message was actually received. And so 0 means yes, 1 means no, 0 is ACK, 1 is NAC. And then there's the actual byte of data, which is what you were trying to send in the first place. And then lastly, the stop condition in which the controller switches the clock and SDA back to high. And so that was a lot of words, and I understand if that's like a lot to like take in all at once, but it's not super important to like understand it right now. But this is just a general overview of how I2C works with your communication device. But we also have like a graphic here that might make you understand it a little bit better. So there's the start condition, which is where you send SCL and SDA down to 0. Then there's the address frame, which tells the controller which peripheral it wants to talk to. There's the read-write bit, depending on like which the controller sets depending on what it wants from the peripheral. And then there's a bunch of ACK and NAC bits to like verify that the process is going well. And then it's the actual like data occurring. And then it stops. Yeah. Okay. So we can have a summary in terms of pros and cons of each protocol. For UART, it's pretty simple and it's widely used by a lot of different devices, including USB, the Arduino, the serial monitor, the HC05, all of these different things. But in terms of cons, we need a baud rate because it doesn't use a clock. It's only one-to-one communication, so a controller can't talk to multiple peripherals. And then you also have to add those bits that you don't have to do when you have an actual clock. And then for SPI, you can have multiple peripherals. So one controller can talk to multiple peripherals. But the downside is I can only talk to one peripheral at a time. So technically still kind of like one-to-one, but not exactly. And then it requires a lot more wiring, and then it's a little confusing. And lastly, we have I2C, which is probably not the best, but like it's another widely used one, in which it has multiple controllers, multiple peripherals, and they can all communicate at the same time. It's also very widely used. And lastly, it has a complex message format, as you saw in the whole ACK-NAC bit thing.
One last thing I'll add is that there's a slight difference as well between I2C and SPI. You'll notice here that when in the I2C diagram, there's only one data line versus in the SPI, there are technically two, right? There's the CIP open, controller in, peripheral out, and then there's the other one. What that means is that you can send data to and from a peripheral between the peripheral and the controller at once, as opposed to having one line when you can't. There's a term for that. The I2C one would be referred to as a half duplex protocol. That basically just means that only one of the two devices involved can send data to and from the other at one time, versus SPI, which would be considered a full duplex communication protocol. Again, it's not strictly necessary for you to know, it's just an extra bit of information.
Okay, any questions after that? Okay, lastly, for chapter 2, it's gamer time. So we're gonna be going over a little bit more about actual Gameduino, your next project. This will be a lot less, I don't know, wordy than the last like 30 minutes, so sorry for that. But we're going a little bit over just some basics that you'll need for making a game. and then talking about the Gameduino and what you'll need for that project.
Consider this a CS 3132 review session.
Not 32.
31.
Yep. Okay, so arrays. So I'm so sorry. This will be better. This is better than what's your project? Like Madness, something.
Oh, madness! My favorite game.
Yeah, better than that. So, just like to remind you, Arduino IDE is in C, right? C. So all you know from like CS, everything that you've learned from CS31, 32, whatever, it's gonna be the same format. You have to have a semicolon after every line. You have to have your curly brackets and everything. And so to create an array, you're gonna have your item type or your data type at the front. You're gonna have a name, and then you're gonna have square brackets, and inside those square brackets indicating how big you want your array. And obviously at the end, like a semicolon, but that's not there for some reason. And so an array you can kind of think of as a list. A list is a different thing entirely. That we don't want to confuse you, but basically imagine it's just a set fixed size length of like multiple data items in a row. So you can't change how many items there are in there. You can't change like the actual like, I guess, integral being of the array, but you can change the individual elements. So let's say you create an array with like 10 integers. You can change what each of those integers are if you want. And so in memory, in terms of the actual memory, if you're gonna take CS33 ever, which I recommend, fun class, but basically, arrays store data consecutively in memory, which means it's really easy to access because the computer, if it has to access some element in that array and then later needs to access another element in that array, it remembers it accessed that. Remembers is like kind of weird to put it, but like it recently accessed that memory, so it's pretty easy to find that memory again. So arrays are pretty cool. They're very easy to access and generally used a lot. Okay, so we have array examples, just different arrays. We probably won't like spend too much time on this, but something that is quite important is going through your arrays. Let's say you want to go through each element for whatever reason. You can use for loops. So a for loop syntax is that you have a for, you have open parentheses, you have this like general syntax in which you have to have a variable that's going to be iterated through. This is the condition, so it's going to continue iterating as long as I is less than 4, and then this is like what it tells. This I++ is telling that at the end of this block of code, it's going to increase I by 1, and then it's going to continue doing it again. So if it starts at 0, it's going to do this with I equals 0. It's going to increase I to 1, and then it's going to go again and do it again until I is 3, because that's the last number before 4. And so you can get a lot more complex if you need to, but this is generally what you'll be using in your project. Also, you can like name this differently if you want to. Yeah.
Pop quiz. The code on Lara's right won't compile. Why is that?
There are no semicolons.
Correct. Okay, we're good to move on.
I was looking at this one now.
I said it was the code on Lara's right.
Oh, wait, I was here for some too. I was like, why is that wrong?
There are circles.
Both of them
Okay.
But the most
The most right.
No semicolons. I was like looking like, oh, did it like access the wrong number of elements? Was it out of bounds or something? Man. Okay, function.
Oh.
Another small group special. Yeah, so functions are there so you don't have to write the same code 2 billion times when you're doing, for example, Arduino. These are there so that you can organize your code. Yeah, that's basically the purpose of functions. They're for you to accomplish a rather complex task and have it bundled into a nice function that you can just call anywhere in your code. The syntax is pretty simple. It's just a return type and then whatever you want to call the function. Typically, you want to call it something helpful, like if you're taking an average of numbers, you might think to call it average. And then it takes parameters. Yeah. Arguments. Any information the function needs to do its job.
And so, I guess more on the return type. If you don't need to return anything, as in like, let's say your purpose is simply just to change, like say you input some parameters, you want to change those parameters, but you don't actually want to return something, you can set the return type as void. And that makes it so that the function doesn't actually return anything. Okay.
Yeah, so here we have a few examples of functions. From brief inspection, it doesn't seem that there's anything wrong with the code here. But yeah, so we have a few kind of different examples of functions with various parameters, as well as return types. Building off of what Laura said earlier, if your function doesn't return anything, return type is void, and you can include just a return statement by itself. I don't know that you necessarily need to do that for Gambino, but again, that depends on what you implement. So yeah, in terms of function uses, you can use those to actually calculate values from other values. For example, like manipulating variables to get something useful out of it. I don't know, for printing stuff out, for playing a song, etc. You can use them for pretty much anything.
Okay. And then lastly, actual Gambuino. And so the main gaming of our project will be using the OLED. So this is the OLED display. It's gonna be like a little, it looks like this, but it's gonna be like a small 128 by 64 pixel screen in which you can create whatever you want on there. It's also unfortunately black and white, so no fun colors, but we're gonna have the OLED. You're gonna have to pick this up from the lab. Again, same as the HC05 because the aux box doesn't come with the OLED. Oh, also, just a side note, if you still have your HC05 and haven't returned it yet, like no rush, but we do need you to eventually return the HC05 because while we do give you the aux box, we reuse the HC05s every year. Same as OLED. Yeah.
Okay.
Don't make us spend more money.
Yeah.
And then secondly, we have the hardware in which we're gonna have the OLED, we're gonna connect everything to our Arduino, all of that. We're also gonna have a joystick to actually play like your game. You're gonna be able to like move things on your screen depending on how your joystick is working, whatever. It's pretty fun. But part two is we're gonna have the software. So for Gambuino, we're gonna ask you to create tic-tac-toe. And so that sounds a little complicated, like to do tic-tac-toe from scratch. Because you have to like create all the pixels, you have to determine like how to actually move everything. So we do have a library that kind of gives you the graphics. You don't have to set that up all by yourself. But the actual logic of the game in terms of checking whether the game has been won, that you have to do by yourself.
Yeah, actually one very important thing I forgot to mention about functions, which is relevant to this project, is that most of the functions you'll need for the first part of your project have already been written by a ops student from a few years back. Those are what are included in the graphics library that we'll be using. So the core of your task for that part of the project will just be to code the game logic.
Yeah.
But as far as the actual graphics themselves, that has been taken care of, at least for the first part.
Okay, and then for joysticks, the joystick is like kind of basically, well, not kind of, it is an integrated circuit, but you don't think of it that way. And so the joystick has left, right, down, up, but also has like press, which is kind of fun. And it works by having two potentiometers. Potentiometers tell you kind of like angle, or like, yeah, relative to some angle, like how you tilt something, right? And so you can use that to be able to actually tell like, oh, I've tilted the joystick so that I'm facing it down. So that means I'm gonna do something based on the fact that I'm tilting the joystick down, right? And so it has 5 pins. It has ground, power, then it has VRX, VRY, and then SW. And so ground and power are pretty self-explanatory. You need to power the integrated circuit. But then VRX and VRY and SW, those correspond to the different directions. So VRX will be left, right, the x-axis. VRY will be the y-axis. And then SW is digital switch. So when you press down on the button, that's gonna be indicated through digital switch.
Before we move on, very quickly to kind of illustrate how this might work for the potentiometer bit, I think we probably maybe covered this in like a previous power-ups, something like that, but yeah, potentiometer, basically you can think of it as a sliding resistor. Basically, you can think of it like this. Let's say you want to move your slider from all the way to the left to all the way to the right, right? And then remember that at the end of the day, what your computer like picks up, how it detects like where your joystick actually is through an electrical signal. If it's an analog signal, it means that it can detect, oh, it's all the way at the left, let's say that corresponds to a value of 0, or all the way to the right at a value of, I don't know, 3 volts, or somewhere in between. So as you slide the joystick from left to right, this kind of potentiometer would change. And based on that, the amount of, let's say, I don't know, current that's going through, or the voltage that you would read off of that pin will also change. And that's how you'd be able to kind of get an analog X or Y axis.
Okay, and then for displays, we're going to be using the OLED, which stands for Organic Light Emitting Diode. There's also in your aux kit the liquid crystal display. This one's like a lot cheaper, which is why it comes actually in a box. And it's pretty long lasting and not as sensitive to when you make mistakes with it. But the OLED is a lot more sensitive, so I recommend being pretty careful when you connect it up, because just like the HC05, we don't want to break it.
Yeah.
But it's also a lot fancier. It has a lot more pixels and they're like a much clearer, which is nice. So you are gonna be able to do a lot more on the OLED than you would if you had the liquid crystal display. Yeah. Okay, and then for the OLED uses I2C communication, which we talked about a little earlier. And so if you remember with I2C, all it needed was the SDA and SCL pins. So all you need to connect this OLED is ground, power, and then SDA and SCL, which you're just gonna connect to 2 analog pins on your Arduino, and then there's a little bit more setup to it on the actual Arduino, but that's basically it. So it should not be that complex. Okay. So, Dreamweedo. We have a couple dates for you to keep in mind. Next Thursday we have session number 1, 6 to 9 p.m. The Thursday after that is for session 2, another 6 to 9 p.m. And then we have our competition on the 12th, which is actually Tuesday. It's Tuesday of week 10, and we decided to make it Tuesday of week 10 because we hoped that if people are crammed studying for finals week 10, hopefully they start on Wednesday, right? So like week 9 weekend, you can cram for for Game Veto competition. Sounds good, right? Yeah. So that's what we're gonna do on Thursday, because also Thursdays we close the finals, and we thought people would be busy.
Guys, please show up to Game Guido.
Please.
We're begging. But yeah, this way not even Smallbrook's weekend finals will be able to get to you before you get to Game Guido.
Right?
So, yeah.
We thought this through.
Yeah.
What if you have a midterm that Friday?
Oh,
Then
that's really
it's
tough.
a whole 3 days away.
Okay.
Maybe like 2 days to study for a midterm.
Yeah.
One to study, one
Yeah.
to make your cheat sheet.
Do you like me study only the night before?
Okay.
Yeah.
Yeah.
I'll come if you bring different types of cookies.
We'll think about it. We'll think. Hey. Let's talk about this later. I'll think about it.
This guy, I told him to get cookies. He went to get cookies, and he didn't think about the fact that some people don't like chocolate chips, or the fact that there's variety in this world, so he bought 24 chocolate chip cookies.
I actually explained the logic behind this. Basically, okay, the problem is all of the cookies are the same flavor, right? But let's say that you have 6 people there, and each person gets 4 cookies. Nobody has a problem if all 4 of their cookies are one flavor, because it's just 4 cookies.
Huh?
And then each person. Yeah.
Who's eating 4 jars of cookies?
Also, actually, we can get 2 separate food things.
Oh yeah, we actually have a lot more freedom with what we want to get in terms
Yeah.
of food, because there's some internal stuff in the department. They don't take like. Long story short, they were making our life very difficult for the past like a quarter.
Year?
Now they've basically given up, and they're letting us do whatever we want.
Yeah. So
So send requests.
as in like we can verbally ask.
Chicken
Actually,
katsu.
chicken katsu?
Okay.